Our project was to verify the designs of the West Point Bridge designer, which we'd been working with for a couple weeks before we built our bridges. And we worked on bridges that had arches rather than beam supports and things like that. And we wanted to find out which design worked the best for our bridge, for the bridges in our class.
Describe how you built this bridge.
We built this bridge using quarter-inch pine strips, and we weren't able to use any nails to connect the different parts together. We had to use wood glue or other methods of like fitting it together like a puzzle piece. We didn't actually end up using those. We pretty much just used the wood glue. We had to like cut our pieces using a bandsaw, and one aspect of our bridge we cut notches in and then like fit it together to make it stronger. So there was a couple different parts.
And what else? With our bridge, we used mostly triangles. Like all of the aspects of our bridge made a triangle, which reinforced the strength of our bridge to allow it to hold more weight.
Why did you pick triangles?
Because you can't change the shape of a triangle due to their angles in the side lengths.
It's the strongest geometric shape.
Very good. Did you know that going into it, or did you figure that out?
Oh,
I
knew that.
yeah.
Going into it.
Yeah. And so what's the ratio of weight? What does that mean?
It basically means that our bridge weighed X amount of grams and could hold X amount of pounds. So the way that you do it is you figure out how many pounds per gram it held. And basically the goal was to try and get it over 1.
And what was yours?
Ours was 1.23.
Yeah. Excellent.
It was the winner.
So you had the best one in the group,
Yes.
right? Very good. Very good. Was your bridge design efficient? How and why?
I would say yes, because our bridge resisted most of the factors against that we were working towards, like twisting and bending and shearing and compression and tension. And the only thing that really hurt our bridge was the shearing. Like and bending. Once it bent too far, it sheared and broke.
Now I noticed when the actual cables moved. So what does that mean?
Well, the way that our bridge was built was that the weight pushed down on the top, and because it was an arch, it caused the bridge to force out on the tables. So a lot of it used the tables. So therefore, when it broke, that force against the tables was gone, so they were able to come back together.
What do you guys think overall of the whole project?
It was fun.
It was a lot of fun. And our bridge was very pretty.
Yep. One problem, though, that we did run into is when we were early on, when we were doing the sides, and we had it glued and clamped, and in between classes, it actually ended up getting broke. How, we're not really sure.
We had to use glue to glue it back together, and it wasn't as strong as it could have been.
So we think that might have been where it broke. So it might have been able to hold more.
Interesting. Initially, if it hadn't changed. Interesting. So, is there anything else you would have changed? That was something that was kind of out of your control.
Right.
Anything that was in your control, is there anything you would have changed differently next time?
No. Like, the only thing we thought of, like, after our bridge broke was that if we could have laminated the arch to be stronger, because that was really the main point of our bridge, was the arch supporting the top of the bridge.
So if we didn't have the limitation of 4 laminations, we could have done more, then those arches would have been significantly stronger and probably been able to hold a whole lot more.
And your percentage would have changed, right? The ratio?
Yes.
Yeah. Yep. So, very nice. Fantastic.